inner city of Port Melbourne to coastal Port C and rural Pekinang area. Yes, we have more than 20,000 kilometers of pipe, 8 water recycling plants, more than 300 pumping stations, and the value of our assets is more than $3.9 billion. So this morning, I have touched on a little bit about why we are so keen to be part of the NICE Hub. So like I said, we have water, we have nutrients, we have other materials, and which they are all significant contributors to the circular economy. And we are facing the pressures of population growth, climate change, water scarcity, urbanization. So we have to do something now. And that's the reason we have built our research partnership with the ARC NICE Hub. So next I'm going to talk about our plan. So you probably all know that the NICE Hub, their work covers the whole value chain from urine collection, urine process, fertilizer optimization, and end user of the fertilizers. So we actually developed 3 main projects which also cover different areas. So the 3 projects, the first one is about impacts of the urine separation on the downstream process. The second one is about new process for nutrient recovery from urine. And the third one is, as Professor Sean just mentioned, is about NICE Loo, which is a futuristic mobile toilet for the technology demonstration. So next I'm going to talk a bit more details of each of these projects. The first one, impacts of urine separation on downstream process. So previously, there are some preliminary studies. They basically demonstrate if we have the urine diversion, then we will have less corrosion on the sewer pipes. So it's obviously because the urine normally, the pH of the urine is normally lower than 7. It's acidic, and we have a lot of salts like chloride, which can corrode our pipes. And meanwhile, the urine diversion can also have some positive impacts on the treatment plant operation. Basically, we remove the nutrients before entering to the treatment plant. We free up the treatment plant capacity, and we also reduce the treatment plant energy consumption. But this is only preliminary studies. What we are going to do with the researchers from the NICE Hub is to further investigate the impacts of the urine diversion on the downstream treatment plant operation. We are also going to investigate the microbial communities and the chemical transformation within the sewer pipe. So the second project is about a new process for nutrient recovery from urine. So these 2 projects you already know. It's 2 well-known processes, URVEL and YOGO, which are developed by Professor Sean and Dr. Stefano. So they are either based on the MBR with the membrane distillation MD process or electrochemical processes. So we are at a very preliminary stage to develop some new process to recover nutrients from the urine, this new integrated process combined with reverse osmosis, our membrane, and some pre-treatment process like fractionation. So we all know that our process has a lot of advantages. For example, we can get concentrated nutrients. We can also produce the permeate, and we don't need chemicals. But we also need to control the biofouling and the scaling of the membranes. So we try to do some new pre-treatment combined with some pre-treatment process to control the scaling and biofouling of the membranes. And by the way, we haven't got a good name for the process. Maybe you can come up with some good names. Please let me know or let our team know. So the third one is about nice loop, a mobile, futuristic public toilet. This public toilet will combine with traditional human toilet and with a living lab, which transfers the human urine to the liquid fertilizer. And we will build this, and we can use it to support our customer engagement and the community events. We can put it, or we can support the councils like a food festival, music festival, or just put it in a hot spot, in the tourism spot during the hot summer. So we hope this is a living lab to research and trial urine transformation to liquid fertilizers. It's an application of treated urine for the urban farming and vertical garden. It's an education center to understand customers' expectation and driving their behavior change. It's a research site to investigate the decentralized urine nutrients recovery system for future scale up. It's an engagement tool to engage local councils, the communities, the agricultural or fertilizer sectors. It will also be an exhibition center to demonstrate our commitment to the circular economy. So I won't talk too much about the technical development of nice loop, which is obviously important. I actually would like emphasize the customer research component of this research, of this project. So how is our community, our customer community's attitude and behavior to the circular economy? What is the best messaging and engagement strategies? How we can influence social media? And how we can promote the use of circular economy process and materials? And can we test the willingness to pay for the future scale up of the circular economy project, such like this? This is all what I have. Thanks for your time. Like I mentioned this morning, I'm really looking forward to unwrapping the onions of the circular economy with all of you. Thank you.
Thank you. So we have plenty of time for questions. Okay.
For ammonia pH 9, you get a lot of ammonia become gas. So how have you considered about the loss of that before you apply to our recover?
You are right, because when you increase temperature or you increase the pH, the ammonia will become a gaseous ammonia rather than stay in the water. But I guess what our pre-treatment fractionation, we are at the, I guess, in the preliminary stage. Probably before that, we should try to recover the ammonia before they become a gaseous components. Any other questions?
Thank you.
Go ahead.
That's right, I'm quite loud.
That's all right.
Thanks. Enrico from Griffith Uni. I was just thinking your questions about, what what's social messaging and everything. I think we can learn a lot from, there's a lot of that research done around the recycled water use, perceptions of what people's concerns were and methods of investigating those that we can translate across to this project, and strategies on how to get that information and how to design really useful sort of experimental social survey work that elucidates exactly what the messaging should be, you know, so that we do it with good quality and publishable results about that evidence for that's the appropriate messaging, and we can certainly translate. There's a lot of us that were involved in that around the Centre of Excellence of Water Recycling on developing those sort of methodologies, so I'd be happy to, I think that can contribute to the social survey work of the project. Just wanted to share that.
This is a really good suggestion, and I think we are aware of that, and you are definitely right. There's a lot of similarities here.
But different.
Yeah,
Okay.
but different. Like you said, because recycled water has been here for a while, and people kind of accept it. Although we are not quite there on the total reuse, but obviously we already widely applied recycled water. But a circular economy for here, urine diversion and recover the nutrients, I think it's still at the early stage development. There's similarities, but probably there's still a lot of knowledge gaps we can investigate, we can study. But obviously, very good suggestions. We can definitely take that, take the suggestions and keep in mind. Thank you.
Lee, just,
Yes,
sorry,
Gary.
with regard to the, I guess that you talked about the downstream impact of taking urine out of the system. Is there any negative impacts of that from a processing perspective within the treatment plants?
This is a really good question. I guess we only talk about the benefits of taking the nutrients from the treatment process, like free up treatment capacity, and also lower the capacity, and even potentially we can lower the nitrous oxide, which is a scope 1 emission from the treatment process. But obviously, when we do some changes, this may have some negative impacts on the bugs, which we rely on it to treat our wastewater. So there's probably something we still need to investigate and quantitatively analyze impacts on the treatment process. You are obviously right. There are definitely questions here we need to investigate.
Phosphate, bacteria, for example, would be one, yeah.
Exactly.
Okay, thank you very much, Leo.
Thank you.
I'd welcome the next speaker, Dr. Jing Guan from Beijing Original Water. Dr. Jing Guan is currently working as a Chief Scientist of Origin Water Technology and a Director of Origin Water International Private Limited. And she is also a Associate Professor at the School of Civil Environmental Engineering at UNSW. So prior to her appointment, Dr. Jing worked at the Center for Water and Wastewater Technology in UNSW as well for 10 years. So has been engaged in research and project management of environmental engineering for more than 30 years. So please join me in welcoming Dr. Jing.
Good afternoon, everybody. Guan from Orange Water International, and today I'm going to talk about application of memory technology in resource recovery. How to move to the next slide? How to move it? Thank you. Resource shortage is a global problem, and once we talk about the resource problem, definitely we will think about like how to recover the resource we already actually used. So in a report called the Living Earth point out, as the natural resource by human actually used exceed their renewable capacity by 20%. So if we continue to do our activity like this without any remediation in the future, after 2030, our living standard will decline about like after 2030. So then everybody, I guess everybody think about like use a different way to recover the resource. And as I'm coming from Orange Water, we are manufacturing membrane, so we will focus on the application of membrane technology in water resources. So today I'm going to talk to 3 applications. One in fertilizer recovery, and the second one is about industry wastewater recycling. And the third one is it's not very positive, but it's still a useful way to recover some lithium from brine and or salt lake. This work actually it's a collaborative project working with Professor Sean's team. So the following data actually provided by Sean's group. I think we're familiar about this whole process. We just try to use some technology to minimize the smiling during during the fertilizer recovery from the urine. So the key points, the key structure of the unit is a membrane, MBR membrane technology. We have run the unit, I think, for 2 years, and also we have some like a product to. It's not product in the market, but we already use for the laboratory plant. So here's some comparison of the fertilizer with commercial fertilizer, and also our product. So from these 3 growths of the plant, definitely the product we actually use from our research is like looks like more leaves, and also looks like how to say, it's like just a leaf rich and also grows very well. So in the next step in the future, we are going to modify the whole process, and also just because we to minimize any risk when we use urine, fertilizer recover from use of urine. So I believe we have lots of things to do. I'm sure we can get like all the result we expected. For the next application is talk about the industry wastewater recycling. So many industry actually developed their technology and also actually discharge lots of wastewater to the lake, or just also some like the water catchment. So even though we have some like a regulation or some standard to limit the discharge of the wastewater into the environment, but actually with the accumulation process, so still have some like wastewater or just a pollutant in the discharge in the environment. So when we do the industrial wastewater treatment or reuse, it's difficult to control the whole process. That's so many questions, so many problems when we do develop the wastewater recycling process, including technical problem and also the high energy consumption, and also for some like just also use other resources. So Orange Water, we developed a solution with microfiltration and nanofiltration, also with RO system for the whole process to meet the requirement of those wastewater, industrial wastewater reuse. And the second example, we do the wastewater recycling is to produce some byproduct during our treatment process. For example, when we do recovery of lithium from brine, to form the lithium carbonate, we also need to add sodium carbonate. But normally when we do with salt licks, we also have some sodium carbonate in the lakes. So we develop that process. We do the lithium recovery, while at the same time we also produce the sodium carbonate. So then we can save money, and also we can actually do the whole process like environment friendly. The next one I'm going to talk about the recycling that like just extract bromine and potassium from seawater. That whole process also like include all the membrane process. So we have the advantage we can develop the membrane especially for industry wastewater recycling. Also we can modify the whole process by ourselves. The last one I'm going to talk about the lithium recovery. The previous two applications actually we really do the a positive job to recycle those resources from wastewater or waste. But this one, lithium recovery, actually it's not that positive. But we really need to fix this problem because we need lithium batteries for our life today. So in this process, we comparing about like lithium mining and extracting lithium from brine. We think about like probably recover the lithium from brine is like more environment friendly, and we probably do not need to damage or just affect the environment around those areas. So these two processes we developed just for lithium recovery. So they have a slightly different, so they also have a different product. That's the actually this is a natural filtration unit we developed especially for lithium recovery. And here's the case study, just the real engineering project we developed in China. And it's not big one, but it's covered all the technologies we developed related to membrane technology. And here's the larger lithium carbonate project that's extract the lithium from salt lake. We developed the absorbent and membrane and the final product. That's the all information I'm going to share with everybody. Thank you for my team and also Professor Jing to provide all the data in this presentation. And thank you for your attention. Thank you for your time.
Thank you, Jing. Thank you, Jing. Yeah. We can entertain a couple of questions.
Thank you, Dr. Guan. Very interesting. I'd like to see the work going on in the industry application. Fantastic. Just interested about the lithium recovery. Did you talk about, you talked about from batteries, but is the process taking feed from like battery waste or salt lake or both maybe? You know, can you, is it you do a similar process?
We only do the extracting the lithium from brine and eggs.
Yeah. Do you think battery waste is going to be a big contribution, or we still need mostly raw supply of lithium? Like I think the IEA predicts something like 10% of the lithium supply comes from recycling, but maybe we can do more. Or not sure what your opinion is for the percentage the battery recycling will contribute to the lithium supply.
Actually, basically, I think lithium recovery from brine or mining lithium, I don't think it's a positive way. So I'd like to do some recycling, like from battery.
Yeah.
That will be the best way for us actually in the future. But we haven't done anything about like battery recovery, recycling work. But I'm sure those kind of absorbent and also the process, I think definitely will consider to develop those applications in the future for the recycling process.
Yeah, no, okay. Thank you.
Thank you.
Yes, fascinating work. You know, I'm just interested to understand if there is a peak lithium conversation going on, and you know the whole issue of, I guess, recycling lithium batteries. We are capturing, I guess, that metal and putting it into batteries. But is there a point where, you know, with mining lithium, when it becomes economic to recycle it out of batteries and extract it from brine? Has there been sort of any work done in terms of the economics of extracting currently from the mining side of things, and when is there a peak lithium moment from mining, and when does that sort of economically make sense to be doing brine extraction and recycling out of batteries, or do we already know that and we're doing it? I guess that's a fairly complicated question.
I understand what you mean, but because we only think about, say in China, we have a special concern about like the resource of salt lake. We have salt lakes actually. They have a chance to do the lithium recovery from those lakes. I also have some literature review about like mining lithium mining. Actually, considering about the economics, probably the price is not mining lithium is not more expensive than lithium extracting from brines. But for the lithium mining, actually, we will restructure the environment around that area. So that will affect actually people living area environment. Also, probably just damage some economic ecology system or something. So considering about that environment friendly, my opinion, if we really need to have some lithium from our natural resources, I just would prefer to do extracting lithium from brine first.
Thank you, Jing. Thank you very much. So we have the last speaker in the first session today, Dr. Behzad Fatahi. Dr. Behzad Fatahi is currently Associate Professor at the School of Civil and Environmental Engineering here at UTS. And Dr. Fatahi is a recipient of several prestigious awards, including Australasia Young Railway Engineer of the Year awarded by the Engineers Australia and the Railway Technical Society of Australasia. His research interest lies in problematic groundwater, ground improvement, soil infrastructure, soil structure interaction, intelligent construction techniques, and optimization of design and construction of the transport infrastructure. So Dr. Behzad also worked extensively on major infrastructure projects, including the WestConnex N8, Ballina Bypass project, and a Brisbane Gateway upgrade project. Please join me in welcoming Dr. Fatahi.
teacher, for a kind introduction. I'd also like to acknowledge category people of Ori Nation whose ancestral land we are meeting today, and pay my respect to past elders, past, present, and emerging. So the type of research that I will be talking about, I guess, is a bit different to fertilizers and so on. So as one of the speakers this morning talked, so I'm civil engineer and I try to find new techniques to stabilize the foundations of the roads, and this is a great opportunity that Sean brought this opportunity to my attention last year and seems quite promising. So that's in collaboration with CINIC group, obviously. So quickly I will talk about problematic soils, what type of problems we have and what we want to improve. So some of the existing techniques and our proposal, what we have, and also I'd like to talk about some opportunities in addition to what we are doing in case we can do some more collaboration. So obviously we know we always like to construct on top of a strong ground, good quality lands, and but it's not always possible considering the increase in the population and urbanization. We need to construct on lands which are not that pleasant. Some of the common ones are soft clays, loose sands, and expensive clays, that if you have got this type of soil under your infrastructure, particularly transport infrastructure, the maintenance cost of those structures will increase, and this is not great for taxpayers. For example, for port construction, the picture you can see here is a land reclamation that we needed to a lot of ground improvement, which is quite expensive, you know, and can be energy intensive in terms of also use of cement. So soft clays are those muddy, you know, the marshy sort of materials that you get, that if you get it under your infrastructure, you end up getting a fair bit of cracks on the roads, or even your railway may suffer damage. So generally, if their strength is low in terms of kPa, kilopascals, less than 25 kPa, they are not good. We need to do something with them, so to avoid the problems you see there. Similar applies to loose sands, such as what you find on the beach. Obviously, is loose sand. Around Sydney, we have a fair bit of sand dunes, and if you have got your infrastructure built on that, again, you can suffer problems. These are some examples of the common or attractive pictures I put there, which are for liquefaction, that if you have got loose sand there, and there is a dynamic load due to earthquake or trains and so on, you may get a problem. As you can see, a structure stands there, but the ground underneath, unfortunately, is not good. The other problem we have is expansive soils. Some soils, when you add water, they expand. So many buildings, cracks that you see in the residential buildings, 1 or 2 story buildings, is because of that. It's just the chemistry of the clay, that water is a polar sort of molecule, will be attached to the surface of the clay with negative charge, and it keeps expanding. So these are problems that we have. So in terms of the expansive soils, it is quite common to find it on the east coast here in Australia, and the picture on the right, what you can see, shows that if you have got this type of clay under the road and it's not treated, you will end up getting these cracks there, and potholes and so on, that all of us we are experiencing these days, particularly after flood. So there are current techniques used to treat those sorts of soils that I mentioned to you. Some of the common ones, or one of the most common one, is the use of chemical binders. The most popular one is addition of cement, that you can see on the left hand side here, that there is a truck going, sprays the cement on the surface, or it might be lime, and then there is a roller coming compacting this material, and then you leave it there, similar to concrete. You can say it sets and becomes strong, and you can build your road on top. Or you may like to, if the problem is deeper, using techniques such as the pictures on the right. We have got a deep cement mixing, that you inject the cement powder or cement slurry, mix it with in situ soil, and create a strong profile, and you build your structure on top. As you can see, cement is one of the common items that we use there, so as a binder. However, we know that there are quite significant challenges in terms of cement usage and production, so it creates very bit of carbon dioxide production of cement, and to be precise, 8% of the world's carbon dioxide emission comes from cement production, just cement production. There are a lot of other challenges in the construction industry, but this is just from the cement production. So therefore, there is a great motivation there to minimize usage of cement and therefore production of cement, so in a traditional fashion. So if you wonder how it works, is that basically cement goes through the cleaning system and then under high temperatures, measures around 1500 degrees, you create the cement and then CO2 would be generated there. So it's energy intensive as well in terms of CO2 production, obviously. So the proposal here we have is that we would like to see those problematic materials that we have, including Bringeley shale that we have here in New Airport in Aeropolis in Western Sydney. So we would like to add treated urine and add the current proposal. The research shows you can add also a bacteria called urease, and then that creates this, some binder in the soil without actually having the cement addition in there. So the urease is an enzyme basically that acts as a catalyst in here that facilitates creation of the carbonate. Probably this is like chemically also, I'm civil engineer, I'm not that great in chemistry, so but this is the mechanism involved. Urea plus water in the presence of the urease, which is a bacteria or enzyme you can say, creates carbonates, and of course byproducts which are not nice in construction industry, including ammonia and ammonium, and then we will